All right, let's dive into one of the biggest puzzles in clean energy right now. How in the world do we make those giant cargo ships that cross our oceans carbon-free? Well, the answer might be hiding in plain sight, with a common chemical that carries its own secret weapon, a powerful gas it can literally create on demand right inside the engine. And make no mistake, the stakes here are absolutely enormous. This isn't just a friendly suggestion from the International Maritime Organization, it's a hard deadline. The entire global shipping industry, the lifeblood of our economy, has to hit net zero by 2050. That's not a small ask. It is a massive, massive challenge.
So that really brings us to the core question. How do you do it? How do you take these colossal vessels, which have run on dirty, heavy fossil fuels for a century, and make them completely carbon-free? We're talking about huge engines, incredibly long journeys, and an immense amount of energy. So where do you even begin?
Well, it turns out engineers have a leading candidate, a sort of flawed hero for our story, ammonia. Yeah, you probably know it from cleaning supplies or fertilizer, but its chemical makeup, NH3, makes it a really fascinating potential fuel, mainly because it has zero carbon. But here's the big hack. On one hand, ammonia looks almost perfect. No carbon atoms means no CO2. Check. It's pretty energy dense, and we already have a global infrastructure to produce and transport it. But on the other hand, it's actually terrible inside an engine. It burns really slowly, very inefficiently, and even worse, it can kick out unburned ammonia and nitrous oxide, N2O, a greenhouse gas that's nearly 300 times more potent than CO2. That's a huge, huge problem. And this isn't just some small technical hiccup. As researchers in the journal Combustion and Flame put it, finding a way to enhance its combustion is urgent. You can feel the pressure in that statement. Without some kind of major breakthrough, pure ammonia just isn't going to cut it for the next generation of ships. So if ammonia can't do the job all by itself, it's going to need a partner. And it turns out engineers have found the perfect candidate to fix that sluggish combustion problem: hydrogen.
Hydrogen is basically the perfect sidekick for ammonia. For one, it's extremely reactive. Mixing in just a little bit acts like a powerful booster, speeding up the flame, making the whole reaction hotter and way more complete. Plus, it's also a zero-carbon fuel, so you're not compromising there. It seems like the ideal solution, but of course, there's a catch.
And oh boy, it's a huge one. Trying to store pure hydrogen on a ship is an absolute engineering nightmare. You either have to compress it in these massive, super heavy tanks, or you have to liquefy it at an insanely cold -253 degrees Celsius. It's bulky, it's expensive, and it's risky. Building a ship with two totally separate, incredibly complex fuel systems is a total non-starter.
And this is where the story gets really clever. Instead of trying to solve this impossible hydrogen storage problem, what if you could just sidestep it completely? What if the ship could make its own hydrogen on demand, using the fuel it's already carrying? This leads us to a truly breakthrough idea: onboard ammonia cracking. It's an ingeniously simple concept when you think about it. You use ammonia not just as the main fuel, but also as the source for its own performance booster. You carry one fuel, but you get the benefits of two. So, what exactly is catalytic cracking? I know, it sounds super technical, but the idea is actually pretty straightforward. You just use heat and a special material, a catalyst, to split the ammonia molecules, the NH3, into their basic building blocks, hydrogen and nitrogen. It's a really clever way to unlock the hydrogen that's already chemically packed inside the ammonia. Okay, so this diagram shows how it all comes together in one elegant system. Most of the ammonia flows directly to the engine, that's your main fuel. But a small portion gets diverted into this little box, the ammonia cracker. And here is the absolutely brilliant part. The cracker is powered by waste heat from the engine's own exhaust. It's free energy. Inside, that heat cracks the ammonia, and the hydrogen-rich gas that comes out gets piped right back into the engine to supercharge the combustion. So really, it all boils down to 4 simple steps. 1, you siphon off a little bit of ammonia. 2, you grab that free energy from the hot exhaust. 3, the ammonia cracks and releases its hydrogen. And 4, that hydrogen-rich gas goes right back into the engine as a booster. It is a beautifully elegant, self-contained loop. So the theory is beautiful, right? It solves the storage problem and the combustion problem in one fell swoop. But this is engineering, not magic. So the big question is, does this clever trick actually work in practice? Let's look at the data. And the numbers are, well, they're staggering.
According to really detailed computer simulations, adding just an 8% hydrogen blend, a blend created from the cracked ammonia, slashes unburned ammonia emissions by 77%. This stuff is often called ammonia slip, and cutting it is absolutely critical. A tiny bit of hydrogen makes a huge difference in cleaning up the exhaust. And hey, it's not just about cutting pollution. That same 8% hydrogen blend also makes the engine way more efficient. As you can see here, its thermal efficiency, which is basically how well it turns fuel into actual power, jumps up significantly. So you're getting more power from every single drop of fuel while running clear. It's a total win-win. Now, here's a really important detail. The gas coming from the cracker isn't pure hydrogen. It's a mix. It's got nitrogen in there and even a little bit of uncracked ammonia. But that's actually a good thing. The whole system is designed to use this raw hydrogen-rich gas directly. You avoid having to add a complex and expensive purification step, which keeps the whole system simpler and more robust for life at sea. And you should know, this technology is not standing still. The success of onboard cracking has really kicked off a whole new wave of research and development, all focused on perfecting these engines for the real world. Take this, for example. This is a simulation of a pretty advanced engine design. See that small pre-chamber up at the top? It's designed to inject that hydrogen-rich gas like a tiny, perfectly aimed flamethrower. It creates this powerful jet of flame that ignites the main fuel in the cylinder much more effectively, making sure it burns as fast and as completely as possible. This is the kind of fine-tuning that's happening right now. So let's just quickly recap the whole story here. We started with ammonia, a promising zero-carbon fuel that unfortunately burns really poorly. We found its perfect partner, hydrogen, but that's practically impossible to store. The brilliant solution, onboard cracking, which lets the ammonia create its own hydrogen booster. And the result is a system that's efficient, powerful, and dramatically cleaner. And that leaves us with one final thought. This isn't just about mixing two fuels together. This is a system where a fuel's biggest weakness, its instability, is turned into its own unique strength. By using ammonia to create the very hydrogen it needs to burn cleanly, you have to ask, have engineers finally cracked the code for zero-emission shipping? It certainly looks like one of the most promising paths we have.